Building underground requires creating a void, but the Earth is constantly trying to reclaim that space. At any significant depth, millions of tons of surrounding rock and soil exert immense inward pressure on any empty volume. Historically, early tunneling projects were slow, dangerous battles against this weight. Engineers used timber to brace the earth, but cave-ins remained a constant threat. Laborers worked in near darkness, hand-shoveling debris and manually bracing walls, literally propping up the earth's weight above their heads with their own labor. Modern infrastructure demands a much higher pace. To dig miles of subway and water lines, engineers needed a way to excavate, stabilize the rock, and build a permanent wall in a single continuous operation. The tunnel boring machine meets those requirements. A fully assembled machine can reach over 600 feet in length, the size of 2 entire football fields. Every machine is a custom-built investment, often costing over $50 million. Because of the specialized engineering required for specific soil conditions, it can take over a year to design and manufacture a single unit. Walking the length of this machine reveals the true scope of the design. A tunnel boring machine functions as a moving, self-contained factory, processing raw rock into finished infrastructure in a single pass. At the very front of the machine sits the cutter head, a massive rotating steel face designed to meet the earth head-on. Embedded across this face are dozens of heavy-duty steel wheels called discutters, which make direct contact with the rock. As the plate rotates, these discutters apply focused pressure that fractures and chips the rock face away. This mechanical force allows the machine to break through solid granite without the need for explosives. Operators carefully calibrate the rotation and thrust to handle changing geology. This allows the machine to chew through everything from soft clay to volcanic rock without damaging its internal components. Grinding the rock is only the first step. The true difficulty is removing that debris while preventing the void from collapsing into the machinery. Directly behind the cutter head, a series of internal conveyor belts scoops up the broken rock or muck and continuously pulls it backward toward the tunnel entrance. To protect the equipment and crew, the machine is housed within a heavy steel cylinder known as the shield. The shield serves as a temporary steel wall. It physically resists the millions of tons of pressure from above, holding the mountain back while the machine continues to move forward. This creates a stable, ventilated workspace inside. The crew can monitor hydraulics and maintain the systems in a safe environment, completely separated from the crushing weight of the earth. By maintaining this pressure, the shield buys the machine the time needed to install the tunnel's permanent structure. At the rear of the machine, a massive robotic arm, called the erector, performs the final assembly. The erector lifts precast concrete segments and positions them with millimeter precision against the exposed rock. As these segments are bolted together, they form a complete, waterproof ring that will eventually carry trains or water. To move forward, a ring of hydraulic jacks at the back pushes off the concrete wall the erector just built. This force shoves the entire machine deeper into the rock. The TBM essentially builds the track it needs to move. This cycle of excavating and building allows the machine to transform a chaotic void into finished, usable infrastructure in one smooth, automated motion. Over months or years, this relentless grinding and building produces a finished, waterproof passage through the earth. This process made the 31-mile channel tunnel beneath the seabed a reality, connecting the United Kingdom and France with a permanent rail link. The work ends with a breakthrough, the moment the cutter head finally shatters the last wall of rock and reaches its destination. Once the work is done, engineers face a logistical problem: how to remove a machine the size of a horizontal skyscraper from deep underground. Because these machines are too massive to dismantle easily and cannot move in reverse, extracting them is often more expensive than the machine itself. In many projects, the machine is steered into a side cavern and deactivated. The crew leaves, permanently entombing it behind the new tunnel walls. These deactivated machines remain deep beneath our cities and mountains, permanent steel artifacts of the engineering.